The last couple of classes, we've talked about either random processes. The case we examined was radioactivity, or random walks. The case we explored was Brownian motion. And we worked on those topics with random number generation and with Monte Carlo methods. In today's class and the next class, so the two classes this week, I want to continue with random number generation and Monte Carlos, but we're going to look at problems of calculating the internal energy of a gas with Monte Carlo methods. And we're going to look at the problem of calculating the magnetization of a solid also with Monte Carlo methods. So we're turning away from perhaps more concrete random processes like radioactivity and random walks like Brownian motion to more abstract random processes where our random process will be a random walk through the states, the microstates of some system like a gas or some system like a solid. I wanted to introduce a little bit of language, a little bit of terminology, microstates, macrostates, multiplicities. I wanted to introduce it in relation to problems that we've already looked at, rolling dice, or more specifically here, tossing coins. That'll get us used to this language of microstates, macrostates, and multiplicities. And then we're going to apply it to the atoms and molecules in our gas today. We're going to apply it to the atoms and molecules in our solid on Thursday. So on this slide here, I've just imagined this old problem that we thought about of throwing three coins, three coin tosses, and the outcomes of the coin tosses, the possible sequences from the coin tosses, just to introduce this language of microstates, macrostates, and multiplicities. So if I calculated here the outcomes of three coin tosses. So at the very top is one outcome, which is three heads. The very bottom is another outcome, that's three tails, and then in between are all the other possible outcomes of the three coin tosses. These 8 permutations for the outcomes of the three coin tosses, those are what we're going to now be calling, what we're now going to be terming as the microstates. These are the distinct microstates of this three coin system where each coin can be a head or a tail. Those are the microstates. The macrostates, the macroscopic states, are the 4 distinct outcomes of getting 3 heads. Getting 3 heads, yes. Getting 2 heads, getting 1 head, or getting 0 heads. So those 4 possible distinct outcomes corresponding to the different number of heads, 3, 2, and 1, are going to be the macrostates. The multiplicities are the number of microstates. Remember, there are 8 microstates in this table, corresponding to each macrostate. Remember, there's 4 macrostates in this table. So, for example, for 3 heads, that's one of our macrostates. There's just one microstate. There's only one way of getting 3 heads. For the case of 2 heads, there's actually 3 microstates. There's 3 ways of getting 2 heads: head, heads, tails, heads, tails, heads, and tails, heads, heads. Those are the 3 microstates for that particular macrostate. So this macrostate has a multiplicity of 3 because there's 3 microstates that have that outcome of 2 heads. The same's true for the case of 2 tails, right? There's 3 ways of getting 2 tails. I've enumerated them here. So the 2 tail state, or 1 head's outcome, has a multiplicity of 3 because there's 3 microstates, 3 ways of getting two tails and one head. And then finally down here, the three tails case, so that's like the three heads case. That outcome, that macrostate has just a multiplicity of one, because there's just one microstate can come out of that, lead to that outcome. If we wanted to plot the multiplicities for the different states, well, here's a plot of the multiplicities for the different states. So the horizontal axis is the macrostates. Individual counts in the histogram are microstates. And the vertical axis is the multiplicity of each of the macrostates. So three tails, zero heads has a multiplicity of one. Three heads, zero tails, multiplicity of one. The other combinations, they have multiplicities of three. If I wanted to calculate the multiplicities of these states, then I could actually, it's just combinations from combinatorics, permutation of combinations. I could use this binomial code, calculate it through the binomial coefficient. So that's three coin tosses. This is 100 coin tosses. So instead of throwing 3 coins, I'm now throwing 100 coins. And you could ask the same questions about throwing 100 coins. What are the number of microstates? How many microstates are there? What are the number of outcomes? That's the number of macrostates. How many macrostates are there? And what are the multiplicities of the individual microstates in the in each particular macrostate? So those are exactly the same questions that we answered with three coin tosses. Remember, there we said that there were eight total microstates, 4 macrostates, and we had multiplicities of 1, 3, 3, and 1 for the 4 particular macrostates. So for the case of 100 coin tosses, the number of microstates is going to be, well, the rule was it's 2 to the power of the number of tosses, so it's 2 to the power 100. There's an enormous number of microstates that we can't write down and enumerate in a table. Well, the number, so that's the number of microstates. So the number of macrostates. Number of macrostates is the number of distinct possible outcomes. Well, one extreme would be 100 heads from your 100 coin tosses. There's only one microstate corresponding to that. Another extreme would be getting no heads, 0 heads from your 100 coin tosses, all tails. Only one microstate that would have that. So with this range of 0 to 100 heads as the possible outcomes, there's 101 macrostates. So we can enumerate the number of macrostates. So that's what I wrote down here. 2 to 100 microstates, 101 macrostates. I could calculate using the binomial coefficients. I could calculate the multiplicities of the different macrostates, how many microstates make up each macrostate. We did that for the 3 coin tosses. That's why we got 1, 3, 3, and 1. If I did that for the 100 coin tosses, I would find that the macrostates with roughly equal numbers of heads and tails, those would have very large multiplicities. The macrostates with the very small numbers of tails, say, mostly heads, or very small numbers of heads and mostly tails, those would have very small multiplicities. In fact, at the far extremes, right, he said that the case of getting 100 heads, well, there's only one microstate that has 100 heads. Case again, 100 tails, there's only one microstate that has 100 tails. So unlike the multiplicity distribution that we drew for the 3 coin tosses, where it was peaked at the center, with tails falling off of the edge, this is with 100 coin tosses, it's very strongly peaked at the center. And it falls off to essentially zero at the extremes of 100 heads or 100 tails. So that's how the distribution changes when you've got a large number of coin tosses. Now, look, we're going to be looking forward to having not 3 atoms or molecules or 3 or 100 atoms or molecules, but much, much larger numbers of atoms and molecules. So you can imagine these extremes of 100 heads or 100 tails are going to be completely negligible. And then the microstates are all centered around the distribution in the center here. Okay. Well, we're going to be thinking about problems like this, but in the context of atoms, molecules, electrons, other particles. And so maybe an analogy would be the spin of an electron to the heads and tails of the coins. If we had 3 electrons, then the spin up or spin down states of each of the electrons lead to 8 different microstates that the 3 electrons could be in. You could have 3 spin ups, 3 spin downs, or combinations in between. So those are the microstates. The possible outcome, the macrostate of the 3 electrons could be, you could have 3 electrons with heads with spin up. You could have 3 electrons with spin down, or you could have other combinations with some up and some down. There would be 4 separate macrostates of the 3 electrons corresponding to 3 electrons up, 2 electrons up, 1 electron up, 0 electrons up. The multiplicities of the states, macrostates of the 3 electrons would be there's one state which has 3 electrons up, one state with 3 electrons down, and then the multiplicities of the 2 other states is 3 for those 2 cases. And we've just enumerated all that for the coin tosses. It's exactly the same for the electrons. Here's the plot of the distribution of multiplicities for the different macrostates. Here's how you could calculate with binomial coefficients the multiplicities of the different microstates. If we had 100 electrons, same idea again. You've got 100 electrons, and you're thinking about the spin states of 100 electrons. There's 2 to the 100 possible states, microstates of the 100 electrons. So enormous number of states of the electrons. There's 101 distinct macrostates of the 100 electrons, ranging from all 100 of them having spins up to 100 of them having spins down. So there's 101 distinct macrostates, and we could, again, with binomial coefficients, calculate the multiplicity distribution for the different macrostates. We'd again find this situation where it's almost impossibly rare to have 100 spins up or 100 spins down. Rather, the multiplicities of the microstates are heavily peaked around an average of 50 up and 50 down for the electrons. You'd have a distribution like this. This given again by binomial coefficients. Okay, so that was just a bit of language. Now I want to move on to using that language in the context of, in this class, the atoms and molecules in a gas. Next class, spin up, spin down electrons in a solid, in the context of Monte Carlos for statistical mechanics. So in classical mechanics or quantum mechanics, we're often working with simple systems, say a single state. We might be thinking about a single atom or molecule or a single electron or proton in classic quantum or classical mechanics. In statistical mechanics, we're typically applying statistical methods, statistical reasoning to collections or assemblies of large numbers of atoms and molecules or large numbers of particles like electrons. And we're interested in using those statistical methods, using that statistical reasoning to determine macroscopic properties of that system of atoms or molecules or that system of electrons or protons. We might be calculating the energy. We're going to do that today. We might be calculating the magnetization of a material. We're going to do that on Thursday. So that's statistical mechanics. Because it is a statistical argument or statistical reasoning, we can use the random number generation and the Monte Carlo methods to compute the macroscopic quantities like energy or magnetization. So it's an ideal case, statistical mechanics, for using random number generation and Monte Carlo methods for calculating interesting quantities. Specifically, what we're going to be talking about is a type of Monte Carlo method called a Markov Chain Monte Carlo method. And we're going to be applying this Monte Carlo chain Markov method to calculating the internal energy of a gas and calculating the magnetization of a solid. So that's our goals. Basically, Markov chain Monte Carlos are random walks. They're random walks, not in ordinary space. You know, we talked about last class, random walk in one dimension, ordinary space, or 2 or 3 dimensions, ordinary space. Markov chain Monte Carlos are random walks through the more abstract space of the microstates of the gas that we're trying to calculate the energy of, or random walk through the microstates of the electrons in the solid that we're going to try and calculate the magnetization of. So now we're not walking through one-dimensional, two-dimensional, three-dimensional space, but we're walking through the large collection of microstates of a particular gas or solid or whatever. Okay. So this is the problem, or this is the question that we're going to work on today. And it's the question of what is the internal energy of some substance, say some gas, given the temperature of that substance or that gas. So, you know, when we measure the temperature of a substance, it is a reflection of the internal energy in that substance or gas. And we want to figure out the precise relationship between the temperature of a gas and the internal energy of a gas. So that's a basic goal. I made a few points on this slide. I'll just walk through them. We know this because we can raise when we raise the temperature of a substance or a gas, heat flows into that substance and gas from some source. We'll call it the bath here, into the sample. The substance is what we call it here. And so that flow of heat is a flow of energy into that substance, raises the temperature. We know if we cool down the sample by the surrounding bath, that heat is flowing out of the sample into the surrounding bath. So we're transferring energy out the sample. And what we're really interested in is that relationship between the energy stored in the sample, internal energy in the sample, and the temperature that we measure for the sample. So how the two. What we're going to do is calculate the internal energy of the sample for a given temperature of the sample. And we're going to do that by this Markov chain Monte Carlo technique. And one of the interesting uses of that is that you can map out the heat capacity of a substance, of a material, of a gas, by a Markov chain Monte Carlo. So heat capacity reflects how much the temperature changes when a certain amount of heat energy is transferred. And so we'll essentially be calculating the heat capacity of our gas as a function of temperature. And the heat capacity of a gas or heat capacity of a substance as a function of temperature is an interesting sort of window or doorway into the microscopic structure and nature of the gas or the substance. So if heat capacity is something you can go in the lab and you can measure the heat capacity by how much the temperature changes when a certain amount of energy is added or removed to the substance. Well, that's giving you a window into the microscopic structure, the microstates of that substance or that material that give rise to that characteristic heat capacity. Okay. So how are we going to do this? I got a few slides now on how this is going to work, how this sort of conceptually works or physically works to begin with, and how we're going to implement it as a Monte Carlo method, a Markov Chain Monte Carlo method. So the basic problem that we're going to be working on is we want to calculate a physical observable is energy in this class, magnetization in the next class, from the microstates of a particular macrostate of a system. So from the microstates of a particular system that is a gas, or from the microstates of a particular system, which is the electrons in a solid. So we want to calculate a physical quantity. Here's our starting point. With the physical quantities valued, so this X here in the little brackets could be the energy of the gas, or it could be the magnetization of the material. So it's the measured energy of the gas. It's the measured magnetization of the material. As a function, say, of the temperature. It'd be a function of the temperature in this class, be a function of the temperature in the next class. This measured physical quantity is given by the value of that quantity for each microstate times the probability that that microstate contributes to the system. So this sum here is a sum over all of the microstates of the system. It's a sum of the product of the value of the measurable or the physical quantity for that particular microstate labeled I times its probability in the macrostate. So this is kind of like a weighted average. Think of the system as being made up of many microstates with many probabilities. Each of those microstates has a value for the energy or the magnetization, and we're going to take those values for the energy or the magnetization, and we're going to multiply it by that microstate's probability within the macrostate. And by taking that weighted average, we'll calculate the energy of the macrostate or the magnetization of the macrostate from the energies or the magnetizations of all the individual microstates. So that's a basic idea of just averaging. If you're going to do that, well, we need to be able to calculate the energy of the microstates. We'll find that that's straightforward. We can calculate the energy of the microstates. Or we need to be able to calculate the magnetization of microstates. That'd be straightforward. We enumerated them for the coin tosses. And we also need to be able to calculate the probabilities for each of the microstates. And we did that for the coin tosses too. So we saw a case with 3 coin tosses or 3 electrons where you could enumerate the energies of the individual states, and you could enumerate the probabilities of the different microstates. This equation here is the Boltzmann equation for the probabilities of the different microstates. So it's a probability that's labeled with this index I that's labeling the different microstates. And it says that the probability is given by this little guy here is e to the minus beta times the energy of the microstate, that's the exponential, these, divided by a normalization factor that's called the partition function. So you probably met this, but if you haven't met this, that's perfectly fine. This is just the equation that we're going to use for these probabilities here. If you want to think about this equation a little bit, so theta is 1 over kT, one of the Boltzmann constant times the temperature in Kelvin. If this and that, so it's that factor beta times the energy of the microstate. So it's actually the energy of the microstate divided by kT in this exponent here. It means if the energy of the microstate divided by kT, if that quantity is a large number, so a high energy compared to kT, then this probability is going to be small. So high energy states are not going to contribute much to the macrostate because their probabilities are going to be small. If this number in the exponent here, the energy of the microstate divided by kT, is a small number, then e to the minus that small number, that's going to be close to 1. So that this is going to have a significant contribution to the microstate. So it's just a factor that is kind of a tunable dial that says high energy states compared to kT won't contribute much to the macrostate. Lower energy states compared to kT will contribute more to the macrostates. The division by z, this factor z, is just the sum of all these probabilities. So it's just to normalize this probability so that the probability of having your macrostate being a particular microstate, if you add up all those probabilities, that's got to be 1. It's got to be found somewhere. So this is just a normalization factor. That's called the partition function. So this is how we're going to calculate the probabilities when we weight the energies, or probabilities when we weight the magnetization of the microstates to calculate the energies or the magnetization of the macrostate. That's the basic idea. This is something I've not explained where this comes from. It's a weighting that comes out of statistical mechanics. It's a weighting that comes out of maximizing entropy. So there's a theoretical basis for it. Okay. So this is more sort of practical comments on using that equation, right? We're going to use the equation to calculate the average energy in terms of the energies of the microstates and the probabilities of the microstates. So just some practical comments on it. First bullet up here, that measured quantity, the energy or the magnetization, is simply a weighted sum of the energies of the magnetizations of each microstate times the probability of that microstate being in the macrostate. So it's just this weighted sum here. These probabilities, as I said, are largest for the ground state, lowest energy state. It's significant for states above the ground state who have energies sort of less than kT. And then it falls off dramatically for states above the ground state with energies above the ground state that are bigger than kT. So the probabilities gets this weighting factor that gets smaller and smaller and smaller as you walk up higher and higher in energy in kind of the units of kT. So that's what causes microstates with energies less than kT. They have significant probabilities for contributing, less than the ground state, but significant probabilities of contributing. The microstates with energies greater than kT, then they have much less probability of contributing, much less than the ground state, and much less than lower excited state. So it's the energy of the microscope compared to KT that counts. If you were to increase the temperature, this is this bullet here, the probabilities for higher energy states to contribute grows. If you were to decrease the temperature, the contribution from higher energy states, if you decrease the temperature, will decrease. So that's this bullet. And then the final point is that this all seems fine, right? You could calculate the internal energy of a gas using this procedure. You could calculate the magnetization of a solid using this procedure. You're going to use this equation for the energy or the magnetization involving the probabilities. You're going to calculate the probabilities according to the Boltzmann factor. That all seems fine, except the fact that for any reasonable system, you've got such a huge number of microstates. Remember, 100 coin tosses or 100 electrons is 2 to the 100 microstates for the electrons or the coin tosses. You've got such a large number of microstates. How can you do this sum in practice? So how could you possibly sum up in your computer program all the contributions from all the 2 to the 100 microstates or however many microstates you've got? This is a computer problem that will never end because it's just intractable. The number of microstates is too large. The way we solve it is not to walk through every microstate of the of a given macrostate. We can't walk through every microstate of a given macrostate and calculate its individual contributions to the energy or magnetization. What we're going to do is randomly walk through a sample of the microstates of the macroscope. And in that way, we're going to figure out the energy of the magnetization. So that's where the random number generation comes in. That's where the Monte Carlo method comes in. We're going to take random walks through the microstates. We're going to be sampling the microstates in a way that will lead us to the energy of the macrostate or lead us to the magnetization of the macrostate, because we simply are unable, it's intractable to try and count up and every contribution from every microstate to the energy of the magnetization of the system. Okay. So this is how it's going to work. And then we'll go to the code and see how it works in a bit more detail. So as I say, the Markov Chain Monte Carlo is the code name for taking a random walk through not 1 or 2 or 3 dimensional space, but through the microstates of a macrostate. And we're going to take this random walk through the microstates of macrostates, microstates of the macrostate of the system, to be able to calculate the value of some observable, like the energy of the system or the magnetization of the system. So that's the random walk we're going to take. The way it works is through these few bullets here. So this is a kind of wordy summary of the Markov Chain Monte Carlo method, the Markov Chain Monte Carlo algorithm. You're going to choose some initial state for your macroscopic system, and you're going to calculate the energy of your macro, or the observable, the energy of your macroscopic system for that state. So supposing you were thinking about 100 electrons, you could choose a initial state that is convenient. Maybe it's just convenient to say, well, they're all spin-up electrons. You could pick that state, and that's going to be your starting point. That's not a very likely state. They're all spin up, but it's just a convenient starting point for you to choose. For say atoms atoms in a box, right? You could pick maybe all of the atoms in the box, or in a simple choice would be every one of them's in the ground state. Every one of these atoms is in the ground state. You could pick that as a possibility. Again, might not be a very likely possibility. It's a convenient place to pick. So anyway, you picked a convenient starting point for your microstates, particular microstate, and then we're going to start working from there, changing that microstate and randomly walking around the microstates of the macro system. So we picked our microstate, and then step 2 is that we're going to take one electron or one atom out of the system of electrons or the system of atoms, and we're going to change its current state to a new state. So we may take, if we pick 100 spin-up electrons, we're going to randomly pick one of them, and we're going to try and change its state. We'll make it spin down. Or if we had 100, atoms in a container, and they're all in their ground state, we're going to pick one of them, and we're going to try and change its state, say excite it. So that's step 2. Once we've decided which electron we're going to try and change from its original state to a new state, or which atom in the container we're going to try and excite from the original state to a new state. Once we've decided which atom or electron we're going to pick and what transition we're going to try and accomplish, we either accept or reject that transition, that change of that electron or that atom, based on a probability that involves that Boltzmann factor that we met. That says that low energy states have higher probability, high energy states have lower probability. The ground state has the greatest probability of sort. So we're going to use that Boltzmann factor. That is a basic sort of foundation of statistical mechanics to either decide to accept the change in the microstates or to reject this change in the microstate. So this is step 3. This is how it works. If the change we're proposing in the microstates is one that lowers the energy of the microstate, supposing we were to de-excite an atom, or supposing we were to change the orientation of the spin of the electron so that the energy of the macrostate was to decrease, then we'll always accept it. We'd always accept that change, a decrease in energy. If we were proposing to increase the energy, so supposing we're going to excite the atom of the gas, or supposing we're going to change the magnetization spin of an electron that increases the energy of the arrangement of electrons, then we will accept it with some probability that is less than 1. And that probability that's less than 1 is given by the Boltzmann factor here. It's e to the minus beta times this change in energy that we're proposing. And if the EJ, the new energy, is greater than EI, the old energy, this means that this is the exponential with a negative exponent, and it will cause a less than 1 probability for accepting that increase in the energy that depends on how big or small that increase in energy that we're proposing actually is. So this will sometimes accept and sometimes decline transitions when the energy of the new state is greater than the energy of the old state. Okay. Then what do we do next? Well, we've either accepted or declined that change. We just go round steps 2 and 3. Again, we'll pick another atom or another electron. We'll pick another transition, excite or decite the electron, the atom, or flip up or down the spin of the electron. And then we'll accept or reject that transition based on these probabilities. If the energy of the system is decreased by that change, we always accept it. If the energy of the system increases, then we accept it with a probability. So we keep doing this, keep doing this, keep doing this, and this will walk us from our initial conveniently chosen microstate. That might have been 100 electron spin up, so a very rare state, or it might have been 100 atoms in the ground state, or a very special state. It will walk us from those special, unusual states to, it walks you to a typical, an average state, which has the typical or average magnetization or average energy for the particular temperature we have the material or the gas at. And so this is a random walk through the states from some unusual special starting state to an average state with the average energy. This process of taking this random walk is it's called a burn-in or a thermalization, because you're taking a initial state that is absolutely not in sort of thermal or energetic equilibrium. It is a special, an unusual state, and you're burning it in, you're thermalizing it into a typical or average microstate in your system. It's like you're walking from, remember the distribution of 100 coin tosses? Most of the microstates are centered around an average of 50 heads and 50 tails. Well, we're kind of starting, if we started with 100 heads or 100 tails, and we make a bunch of these Markov chain steps, we're going to walk our way inwards from 100 heads or 100 tails to a distribution where most of the microstates are, where you've got on average about 50 heads and 50 tails. So we're just taking this random walk into where the distribution of most states are, and then calculating the outcome for the energy of the magnetization of the number of heads and number of tails. Okay. This is just some comments on this that I wanted to emphasize, because I've already kind of said them, but I just want to stress them a bit. As we take this random walk through the microstates, we're going from an initial state which have configuration which might have a very, very low multiplicity. 100 heads is a very low multiplicity. To a state that has a very high multiplicity. So having 50 heads and 50 tails has a very high multiplicity. So just by walking randomly through the system, we're going to walk from this very low multiplicity state to this average high multiplicity state. So that's the basic idea. The upward transitions, as I said, those get penalized. The downwards transitions don't get penalized. That's the key to walking from the low multiplicity to the high multiplicity states, is that particular weighting. That particular weighting, if you want to think about it, is basically implementing the Boltzmann factor in the calculation. The Boltzmann factor is a weighting based on energy, and this is how the Boltzmann factor comes into the Markov Chain Monte Carlo. So these weightings here. That weighting is consistent with the Boltzmann factor, which is the probability of different microstates as a function of the energy of the microstates. After we've taken a bunch of steps through this abstract microstate space, then that process kind of burns us in, thermalizes us to a typical average microstate. and we can extract that it's equilibrated us to that typical or average state, and we can extract the energy from that, or the magnetization from that state. So that's the basic plan. Okay, I think we'll then go on and do an example of it, because maybe it'll become clearer how it works through an example. So the example I want to look at in today's class is we're going to imagine a box, and we're going to put a quantum mechanical particles in the box. They're going to be distinguishable particles. We won't have to worry here about the bosons and fermions. So we'll put, to avoid that for the moment, we'll put just distinguishable particles in the box. We're going to put n of them in the box of a certain size, where the energy levels of these quantum particles in the box is given by this little equation here. So this tells us the energies of the states of the quantum mechanical particles in the box in terms of the quantum numbers of the states. That's the lowercase n, the dimensions of the box. That's the L here. It's the width of the box, and the mass of the particles that we're putting in the box. This is just a familiar formula for a one-dimensional infinite square well. The energies of particles in an infinite square well have this expression here. So that we need an expression for the energies of the states in the box, because we've got to calculate the energies of our particles in the box and add them all up for each microstate. So we need this formula. So that's an important thing. If you're going to be calculating the internal energy of the gas, you need to know the energies of the individual microstates. This can tell us the energies of the individual microstates. In the next class, we're going to be calculating the magnetization of some solid. We need to know the energies of the microstates corresponding to spin up electrons, spin down electrons in that solid. We're always going to be needing a formula for the energies, and this gives us here a formula for the energies of the atoms in our box, or the atoms in our gas, in our container. So we're going to use that. Most importantly, as we perform this Markov Chain Monte Carlo, what are we doing? We're picking atoms in the gas, and we're trying to raise their energy or lower their energy, change their microstate. So we need to know the change in energy when we raise an atom to a different microstate, or we decrease an atom to a lower microstate. So what's of most practical importance in the Monte Carlo method, Markov Chain Monte Carlo method, is the change in energy when we promote or demote an atom to a higher or lower excited state. So I took that equation for the energy of the states in our one-dimensional box, and I calculated that from that the change in energy when I increase n by 1 or when I decrease n by 1. So this is raising the energy of the microstate. How much energy will the microstate go up by if I take one atom and promote it by a principal quantum number? I increase the principal quantum number by 1. So this is if you figure that out, this is the change in energy. This is the other possibility. The other possibility I'm going to allow is that I'm going to decrease the principal quantum number of the atom by 1. So that's lowering its energy. And if I do that, the change in energy is going to be negative now. It's going to be a decrease in energy that's given by this little expression here. These are the two energy changes that I'm going to be concerned with. Look, this is a choice that I made in my particular Markov Chain Monte Carlo for my particular gas, right? I said my atoms and molecules can only be lifted up by a principal quantum number by 1, or they can only be lifted down, principal quantum number by 1. So it's just a choice. I'm making in exploring my distinguishable particles in my one-dimensional square box. So these are the two changes in energies I need, and this would allow me, if I was to promote a atom from the ground state to the first excited state, n equals 1 to n equals 2, then I could calculate the energy need. If I was to demote a atom from the first excited state to the ground state from n equals 2 to n equals 1, I could calculate the decrease in the internal energy of the gas. Okay, so now I'm going to get, we're just going to need those two equations, basically. Well, these two equations and the equation that I first showed for the total energy. I go to the code. Okay, so this is my code. There's basically one cell that does the calculation. Let me just set it running. Set it running now. Some of it takes a while. Actually, that is a little too long. But you know, we are going to have a system of a large number of atoms, microstates, and we are going to take in terms of steps, a lot of steps on our random walk through the microstates, because we've got to ensure that we take a long enough walk through the microstates that we burn in to the sort of average state, we equilibrate, we thermalize. So this is a Monte Carlo calculation which simplifies the procedure for calculating the internal energy of the magnetization at the cost of a lot of computational work to take this random walk through the microstates. I need some, well, obviously KT was a key ingredient in our calculation. We're going to calculate the energy of our gas as a function of the temperature. So we need the temperature. And KT, Boltzmann constant times the temperature, is the weighting factor in the determining the probability is likely or not likely of the individual states. So I need the Boltzmann constant, I need the temperature of the gas. I've just put room temperature here. And then calculating KT. These three lines here are the energy of the individual atoms in each of their microstates, or the energy of the entire macrostate. That's the sum of the energies of the atoms in their microstates. That depends on the mass of the particles, the size of the box, and its quantum gas Planck's constant. So I filled in those quantities. Look, I picked the mass of a helium atom. I picked the size of the box to be the scale of an atom. Those I'm just picking examples here. There's nothing special about those numbers. So those are just examples for our calculation. So we're going to put quantum particles because they're characterized by their energy distribution of quantum particles in a one-dimensional box of mass about that of the helium atom in a box that's width, it's one-dimensional box, it's about the size of an atom. So that's what I'm setting up here. Then downstairs here, scroll down here, is where the real calculational work starts. I'm declaring a list here, energy. I'm going to, for each state on my random walk, I'm going to record the energy, and I'm going to create a list of energies for my random walk through the microstates of a gas. That list of energies will be kind of the trajectory that I take in energy as I walk through the microstates of the gas from a very rare microstate to a typical average microstate as I burn in or thermalize. So this is just initializing, that's what EI will mean, the energies of each step. Here's going to be my starting energy. The starting energy is that equation for the energy of a particle in a one-dimensional box. That's what all this is. And that involves the principal quantum number. Here's my initial principal quantum number that I'm setting up here to be 1. So I'm saying to begin with, every particle in my box, 1,000 particles are in the principal quantum number n equals 1 state. They're in the ground state. So, you know, it's a very special arrangement. I'm calculating the energy here of that state for every particle in the ground state. And I'm putting it in, this is the first quantity I'm appending in my energy trajectory here. And I also up here defined an array which records the principal quantum numbers of every atom in my gas. Okay, so this is an array here of size n, the number uppercase and the number of atoms in my gas. And I'm setting it to the initial quantum number, which is 1. So coming out of these lines here, what have I got? This is sort of setting up the initial conditions. What I've got is I'm doing a calculation with 1,000 atoms. What I've got is that every one of them I'm starting in the ground state, n equals what principal quantum number 1 state. I've got an array of the size 1,000 that records the fact that every one of those atoms is in the ground state. So it's an array of 1,000 ones. I've got a list that I'm going to build that contains the energy after each step. I've just got the energy in the first step there that corresponds to the sum of the energies of every atom in the ground state. So that's the point I'm at here. Okay, now we get on to the random walk. And the random walk, let me roll this up a bit. Is that too small at the back, or is that okay? It's good. I made it this size, so I can fit the whole random walk in this little region. My random walk, I pick a number of steps that I'm going to take. And I picked 200,000 steps. Now I didn't pick 200,000 steps completely randomly. I picked it by exploring the problem a little bit. If you calculate the energy for a certain number of steps, you'll see the energy changing, and you'll see it burning in and thermalizing. And by looking at the energy changing and thermalizing and burning in, I picked 200,000 steps because I was convinced that I'd fully burnt in or thermalized by those 200,000 steps. So that's how I chose that. That time to burn in and thermalize depends on the number of atoms that you're picking, depends on the state that you started with. So it's not just one choice. You might have to adjust it, change it, depending if you increase the number of atoms or if you change your starting state. So anyway, I got 2,000 steps, and then I just got a for loop through those 2,000 steps. So now we're in the for loop, understanding that we're going to go through this 200,000 times. First thing I do is generate a random integer. I generate a random integer from 0 to n. It's just picking one of my atoms from 0 to n, or from 0 to n minus 1. So I'm just picking out of the 1,000 atoms a random atom. Maybe it's atom number 17 that I picked. That's the atom that I'm going to I'm going to change its state. I'm going to then go on and change the state of that atom. So next line here is I'm going to randomly choose, after picking an atom, I'm going to randomly choose between these two basic choices, which is, am I going to try and excite the atom, increase its energy, or am I going to decite the atom, decrease its energy? And right now, I'm just picking 50-50. I'm just going to say 50% chance by a random number that I'm going to try and excite, and 50% I'm going to try and decite. If it's less than 0.5, then I'm going to try and excite the atom. If my random number is greater than 0.5, then I go in this else statement here. I'm going to try and decite the atom. Either way, if I'm going to excite or decite, what I'm calculating in these little codes in the if statement and the else statement is the change in n, and most importantly, the change in energy. So this is where I use those. Remember, I wrote down the equations. We don't often write these equations down for the infinite square world. It's the change in energy if you promote by one unit of principal quantum number, or demo by 1 unit of principal quantum number. So I'm calculating that change of energy upstairs here. This is when I'm exciting, and downstairs here, this is when I'm deciding. Okay, so coming out of this block of code, knowing I'm changing this atom state, and I'm either going to try and excite it, or I'm going to try and decide it, and I know the energy costs for exciting or deciding. So now we hit this line here. This line here actually just stops you immediately in doing that transition, change in the atom state, for one special case. The special case is, well, look, if the atom's in the ground state and you're thinking that you're going to de-excite it, that's a physical impossibility. So I don't want to try, the first thing I said, I don't want to try and decite an atom that's in the ground state. So this if statement here, you only get through this if statement. This if statement is only true if you are not trying to de-excite an atom in the ground state. I mean, that's a very special case. This stops you from de-exciting an atom in the ground state. So let's assume we're not trying to de-excite an atom in the ground state, then we're into this bit of code here. This bit of code here, this particular if statement, is where I implement, we said that we don't treat excitations and de-excitations, we don't treat them equally. If it's a de-excitation, I'm always going to accept a de-excitation. If it's an excitation, I'm not going to always accept an excitation. In fact, I'm one that excites by a large amount compared to KT, probably won't accept it. One that excites a small amount with respect to KT, I probably will accept it, but the weighting of whether, or the probability factor, is determined by that Boltzmann constant. And so you see here, I'm generating another random number, and this another random number I'm comparing to the Boltzmann factor. If it was an energy decrease, if DE is negative, then this exponent is positive. And this is always going to be greater than this random number from 0 to 1. So if it's a decrease in energy, this always is true. I always accept the transition. If this is an increase in energy, so if the future state is greater in energy than the current state, the DE is positive, that makes the quantity in the exponent here negative, that makes this less than one. So this is where there is a chance that I accept it or a chance that I don't accept. So this gives me only a probability less than one of accepting upwards increases. So based on either if it's going down in energy, de-exciting, I'm going to accept it. If it's going up in energy, then I may accept it. If I do accept it, I then change the microstate. So I'm going to change the principal quantum number of the system because that's what I propose to do. I'm changing the principal quantum number of the particular atom in the system that I proposed. And then I'm going to change the energy of the system by the amount dE corresponding to this excitation or de-excitation. So this is where I finally actually make the change, if I'm going to make the change. Once I've done that, I store the new energy. So this is the next energy of my random walk through the material. And then I go on to the next step. And I repeat this. Pick another atom, decide whether I want to try and increase or decrease its energy. Calculate the energy change for the principal quantum number change. Accept or reject the energy change in the case of upward increases in energy. Always accept it in case of decreases in energy. That's where the Boltzmann factor gets built in to my calculation. That's where statistical mechanics gets built into my Monte Carlo. Without that Boltzmann factor there's no statistical mechanics and no physics in my calculation. And I just keep doing that, and I do that many, many times. And then I come out of that, and all I've got left is a little bit of plotting here and a little bit of printout. I'll say one thing here. Well, let me return to this line here in a moment. Let's look at the plot. So on this plot are the 200,000 steps that I took through the microstates of this macro system at a particular temperature. The vertical axis is the energy. And so what are we seeing here? Well, we're seeing that I started in a microstate over here that had every atom in the ground state. And then as I started taking this random walk, I started to increase the energies, right? As I kind of thermalized, as I burnt in to the temperature of the system. So as I'm walking up here on these early steps, right, I'm doing a lot of promoting of electrons to higher energies. Remember, I'm starting out in the ground state. I can't push them any lower in energy. My choices are tending to push the energy up of the electrons to begin with. And so the energy is growing and growing. But then later on, right, it seems now I'm getting an equilibrium. This is where it's equilibrated. And each time I'm changing the state, well, sometimes I'm going up in energy and sometimes I've gone down in energy. So this is where I'm it's like if I walked from 100 heads starting point to the case of around 50 heads. Once you get to around 50 heads, your chances of increasing the number of heads or decreasing the number of heads is sort of just statistically fluctuating. Increasing the energy or decreasing the energy is just statistically fluctuating. And so this corresponds in joules to the internal energy of the gas. I've calculated the internal energy of the gas there. When I wanted to quote an energy for my gas, I took the last 10,000 values for the energy of the gas in my random walk. I said, so this is again somewhat arbitrary. I said, By then I've thermalized. I'll just take the last 10,000 values of the energy and average them. I could have taken the last one, right, as some sort of representative energy, but I thought I'd just average the last 10,000. And so I calculated that energy, here, and I printed it out. And so this is this 2.4 times 10 to the minus 18 joules. I actually compared it to a sort of rule of thumb, right? A rule of thumb for in statistical mechanics is that for every degree of freedom, the energy is 1/2 kT. Now I've got n degrees of freedom in my one-dimensional box because I got n particles in my one-dimensional box. So I might expect, based on that kind of rule of thumb, that the internal energy is what n times 1/2 kT. So I also calculated n times 1/2 kT here. So that's 2.0 times 10 to the minus 18 joules, rather than 2.4 times 10 to the minus 18 joules. So the numbers are similar, but they're not exactly the same. But for example, that rule of thumb doesn't really account for things like 0-point energy. And I've got 0-point energy for my gas, because there, even in the ground state, there is an energy of my particles. It also doesn't really account for the distribution of the excited states in the gas. You know, I've got a pattern of excited states that corresponds to infinite one-dimensional square well, but what would it do if I had a harmonic oscillator, one-dimensional harmonic oscillator? It would be a different distribution of states, and you get a different internal energy. So it makes sense that it's about 1/2 nkt, but we shouldn't expect it to be exactly 1/2 nkt, because the internal energy, the relationship between the internal energy and the temperature, which is basically the heat capacity, is a window into the microscopic nature of our gas. And our gas happens to be n particles in a one-dimensional infinite square well with a particular distribution of states. So we're seeing that. If I was to raise the temperature, let's go back up here. Well, let me show you one other thing, right? Before I raise the temperature. Well, now I'll go do this really quickly. I started in a ridiculously extreme state of every atom in the ground state. And when we thermalized, we must have, on average, increased the energies of those states. This is the principle, this graph here on the left is the quantum number of the 1,000 atoms in the box after I let them thermalize. So remember, they all started in n=1, but you see that there's some distribution of them now in, up to n=8 or 9 or 10. This is a histogram of the states they're in. So there's a lot in n=1, but there's even more in n=2. There's a lot in n=3 and 4 as well. So this is the distribution of the states. If I look at that distribution, I say typically I'm in a state around 3 or something like that. Maybe 3 is the mean. So maybe I would have had a shorter burn-in if I picked up here. Let's put everything in the state 3 to begin with. It's closer to the outcome of my calculation. Let's run this. If I run that, my burn-in, is starting energy that's much closer to the true energy. And I burn in more quicker. n=3 is still lower. I still had to add some energy, but it was a closer approximation to the corresponding state at that energy. Of course, if I was to raise the temperature, so the temperature of the surface of the sun, I think, is 5 5,000 Kelvin. Well, we see now that, of course, the internal energy of our gas will be much larger at 5,000 Kelvin. And we see that even these 2,000 steps, 200,000 steps, right, were insufficient yet to equilibrate. I started with them all in principal quantum number 3, but I would have to have many more steps to equilibrate. And so I'm just playing around here with some of the numbers in this calculation, but you could see once you set up this little framework, which is not a complicated code, you can explore the properties of a gas as a function of the number of atoms in the gas, the temperature of the gas, the mass of the gas atoms, the heat capacity of the gas in a whole variety of different ways. It's a very flexible approach to statistical mechanics.